Right. Okay, thank you very much for the introduction, and also thank you to all the organizers for giving me the opportunity to speak here, and also for giving me the first slot of the day. Yay, good afternoon from Japan. And the main result of this talk is that the three strict omega categories on the simplices called the Orientals are also the three weak omega categories on the simplices. So here, when I say a weak omega category, what I really mean is, well, what's called a weak computational set. But I mean, what is it meant to be? Well, so a strict omega category is a category-like structure, but where you have 0 cells, 1 cells, 2 cells, all the way up to infinity, with the usual sort of unitary and associative compositions, and also satisfying the interchange law. And so a weak variant of that should be, well, the same sort of thing, except that all those axioms only hold up to coherent invertible higher cells, whatever that means. But, well, a weak computational set is, well, a simplicial set together with extra something something. So what is, like, why such a thing called a weak omega category? Well, I mean, so how we should really think of these things is that these weak computational sets are not really themselves the weak omega categories, but they are rather the simplicial nerves of these weak omega categories. So we think of a weak computational set X as being of this form, the nerve of some weak omega category A, although it's pretty hard to write down a definition of weak omega category in the usual globular way. So here somehow we are sort of directly dealing with what should be the simplicial nerves without defining the thing that we are taking the nerve of. So it's sort of a funny thing happening here, but that is, well, anyway, that's what I mean by a weak omega category. That's a simplicial set together with, well, extra something. And I mean, I'm going to sort of explain what the extra something is later. But anyway, so it's a simplicial set. So we can talk about the simplices in there. But if so, such X is to be thought of as the simplicial nerve of some A, then an n simplex in X should be thought of as a map, well, out of something into this omega category A. And what is this something? Oh, that something, well, it should be a weak omega categorical realization of the n simplex. And here we are thinking of these simplices as maps out of the Oriental, which I'm going to also, well, sort of define later. And, well, yeah, so anyway, this is how we think about these things. But, I mean, we can also, I mean, because X is, well, a simplicial set, and n simplex in X is also, by Yoneda, just a map out of delta n into X. So by sort of comparing these two things, you can see why, I mean, this result should be true, right? So, so mapping out of delta n into a weak omega category X should be the same thing as mapping this Oriental into A. So somehow this main result is a sanity check in a sense for what we're doing, although the actual proof involves some non-trivial combinatorics, and later in the talk I will sort of give you a flavor of the sort of the combinatorics that goes into the proof. Oh, by the way, here when I say a map, what I really mean is a weak map, so like something like a pseudo functor, but, well, only infinite dimensional. And so in this result, when I say free strict omega category, I mean with respect to the strict maps. And here when I say free weak omega category, I mean with respect to the weak maps. And that's why this holds. Usually the free strict thing is too strict to be the free weak thing, right? Anyway, so this is sort of, I guess, the context around this thing that I've proved. And if you, well, know about these things, then the actual precise statement is, I mean, it's a bit stronger than this, but well, essentially what I prove is that the nerve of the Oriental is a 5-rank replacement of the n simplex in varieties model structure for computational sets, although you don't really have to know exactly what this sentence means for the rest of this talk. So let me start the actual talk by first describing these Orientals. So the original actual definition is a bit too much combinatorics for a 20-minute talk, but let me give you just an informal definition, which should really be a theorem. But anyway, so this nth Oriental denoted by this ON is I said this is the strict omega category freely generated by the n simplex, but exactly what does that mean? Well, at least a little more precisely, this Oriental is freely generated by those atomic or generating M cells, which are in bijective correspondence with the injective maps from M to N in delta. Here are the pictures of the Orientals up to dimension 2. So, in dimension 0, there's only one injective map into 0, namely the identity, which gives us this single zero cell. So, O0 is just a terminal omega category. And there are, two injective maps from 0 to 1, giving us these two objects or two zero cells. And we also have the identity giving us this interior 1 cell. So O1 is just a single arrow. And similarly, there are 7 injective maps into 2 in delta, giving us the triangle. So, basically the idea is to get the nth Oriental, you draw the picture of the n simplex, and then you regard each m-dimensional face as an m cell, and then you sort of freely generate a strict omega category from there. And here is the generating data for all 3 if you are curious. But anyway, so these Orientals, you can construct them this way. And so they define a co-simplicial object in omega cat. So we can define the simplicial nerve of those omega categories by just mapping out of those things. This is the usual sort of nerve construction, but this particular nerve is not full. So in some sense, this nerve functor doesn't quite capture all of the omega categorical structure. And here is an example. So as usual, by left-hand extension along the unit embedding, we get a left adjoint to this nerve functor, and then we can evaluate the unit of that adjunction at the 2 simplex. That unit goes from delta 2 into the nerve of the second Oriental. But this 2 simplex is itself the nerve of something, namely the commutative triangle. So now we have a map from the nerve of something into the nerve of something. But if you look at what it does, it's sending this commutative triangle here to a non-commutative triangle in here. Such a map doesn't come from an omega functor. So this is an example of a map between nerves of omega categories that doesn't come from an omega functor. So this exhibits that the n is not full, so somehow we are losing too much information. And there are at least 2 ways to make the nerve full by sort of equipping the nerve with extra something. So one solution is to equip the nerve with extra data, which would remember which of those simplices had identity as their interior. So for example, in the nerve of this commutative triangle, this particular two simplex had an identity in the interior, whereas its image in the nerve of the second Oriental didn't. So if we equipped those nerves with this extra data, then this map wouldn't be a valid map between those things. So in that case, the nerve of the commutative triangle would be different from this generated 2 simplex. Anyway, so this leads to marked simplicial sets and the notion of complicial set. So that was originally introduced by Roberts, who conjectured that there should be sort of equivalence. So a suitable nerve functor should provide an equivalence between omega categories and those complicial sets. And that nerve functor was then constructed by Roberts. He constructed the Orientals, so mapping out of those. gave us the nerve, and then Verity later showed that that is indeed an equivalence. And so this is somehow the more well-known of the two solutions that I'm going to talk about. And so this less well-known one is instead of remembering the identities, we can try and remember the pasting or the composition operations in the nerve. So this time we are equipping the nerve with extra structure, and this leads to the notion of sets with completion identities of Steiners. And also in this work, I sort of mix these two solutions in a sense. So, okay, so the main result is about weak omega categories. And, well, naively speaking, to get a weak notion from a strict one, what you do is, well, you see every equality or every identity by an equivalence. And that sort of thing is easier to do when you have direct access to what should be the identities. So, as I mentioned, well, as I said on the first slide, the notion of weak omega category that we're using is basically a weak variant of this solution one. But if you think about what that statement actually says, it says that if you start with the n simplex, and if you compose or paste all the things in there, then you get the nerve of the Oriental. So somehow, although the right language in which to phrase the statement is that of completion sets, the content of the statement has got more to do with the pastings, which is easier to deal with using these sets with completion identities. In the actual proof, this is somehow the main point of view that I use. So in the remaining, 8 minutes, I'll sort of talk about this solution too, mostly, and sort of that should hopefully give you a flavor of the combinatorics that you might find in that paper. So, right, so the combinatorics is, of course, to do with the nerves of the Orientals, but the nerve functor itself is defined by mapping out of the Orientals. So the simplicities in there are just the omega functors between the Orientals, and also Steiner gave a really nice and combinatorial description of those things, and this is somehow well suited for, especially when you for talking about the sets with completion identity structure on the nerve. Anyway, so the projection goes like this. So there's a projection between the omega functors between these Orientals OM and ON, and certain formal linear combinations of maps in delta from M to N. I mean, not all such linear combinations correspond to omega functors, only those satisfying certain conditions do. But before stating these conditions, let me give you the intuition behind this projection, which is that any such X, so this is a linear combination of maps in delta, should be thought of as the pasting of the positive terms in it along the negative ones. Example, so I haven't given you these conditions, but once I've given you the conditions, you can easily check that this particular linear combination satisfies these conditions. And so this is a linear combination of maps from 1 to 2 in delta. So this should somehow represent an omega functor from O1 to O2. So an omega functor from an arrow to a triangle with a 2 cell in the middle. And according to this intuition, you should think of this as the pasting of the positive terms, which are 0, 1, and 1, 2, along the negative one, which is 1, 1. So it should look like the left edge 0, 1 and the right edge 1, 2 pasted along the vertex 1. So indeed, this particular linear combination corresponds to the omega functor picking out this composite of the two generating one cells. And so with this intuition in mind, we can look at the conditions in this theorem and sort of try to make sense of them. So the first condition here is that the sum of the coefficients, so this x alpha is the coefficient of alpha in x. So the first condition is that these coefficients sum up to 1. And what this is saying, according to this intuition, is that, well, we are basically pasting k plus 1 things along k things for some k. And I mean, so if you think about what we are doing, we are sort of pasting many, well, constructible things to get a constructible thing. So that should be the right numbers of things, right? If this number is too high, then you are trying to glue too many things that you would probably end up with a disconnected thing. Whereas if this number, if the sum of the coefficients is too low, then you are sort of gluing things too many times that you are creating a non-trivial loop. So that's a, well, justification for this condition, at least one that I came up with. And well, the second condition is, well, much harder to pass. So maybe just ignore this condition. I mean, don't try to like actually read this condition, but if you sort of stare at it for long enough, then you can figure out that what it's saying, according to this intuition, is essentially that if you are pasting p cells along some gamma, then that gamma should be part of the boundary of those p cells. So its dimension should be strictly lower than p. So hopefully that sounds reasonable enough. And also anyway, so Steiner proved that these omega functors correspond bijectively to the linear combination satisfying those things. And well, I mean, if you know about his work on augmented directed complexes, this is where this comes from. And I mean, you can sort of directly deal with these chain complexes if you like. And that's what Gagne, Osonova, and Rovelli did to prove something slightly stronger than this Maehara result here. But I don't know, I found this combinatorics nicer personally. But anyway, the point of expressing those omega functors as a formal linear combination, well, at least one of the good things about this is that, well, being linear combinations, we can add and subtract things, right? So this is just the same intuition from the previous slide. But now this pasting, you can make precise in the following way. So take two, well, n simplices in the nerve of the nth Oriental. In other words, take two omega functors from On to On, and suppose that they are composable in this particular sense. So the K-minus first phase of X is equal to the kth phase of Y. Then, well, we can just paste them like this. So this is just X plus Y minus, well, a degeneracy on the common phase. And I mean, this is exactly the pasting of X and Y, pretty much according to this intuition. And so this is indeed the pasting in the sense that you can make precise. Well, there are actually somehow two slightly different ways of making that precise, but one way is to sort of observe that there is a simplex of one dimension higher with those extra degeneracies sprinkled everywhere, witnessing that X and Y do indeed paste to this thing, in the sense that if you look at the right faces of this n+1 simplex, you find X and Y and this pasting arranged in a sort of way. But anyway, the point is that via that bijection of Steiner's, we can express the pasting operation as essentially as addition, and so that way these operations are easier to deal with. So using that, we can go back to the original theorem and prove it, except that well, so this, I mean, the precise statement of the theorem is in the language of computational sets. So we have to somehow, I mean, connect the two viewpoints. That basically amounts to observing that the two views yield the same notion of identity, which we can make precise this way, but this statement wouldn't make much sense unless you already know about computational sets. And also, they yield the same notion of pasting, again, in the sense that, well, I haven't really described in this talk. But so yes, but anyway, so the point is that they do capture the same notions of identity and pasting, so you can combine them and prove this main result. And well, that's the end of my, I don't know, 20 minutes, and I leave these up for the question time in case anyone wants to read it. Okay, thank you very much.
Thank you, Yuki. Perfect timing. Is there any question or comment? Let's see. I'll look at. Well, there's a question. There's a question.
Well, thank you, Yuki, for your talk. It's very nice to see you. I mean, I don't know much about those mathematics, but since you spent so much time giving us very nice intuition about the work that you did, can you also just recontextualize again, if you did it, the result itself, like give us some framework around it?
Wait. Hi, Francois.
You can answer. Did you hear the question?
So, well, okay. So I couldn't quite hear the last part. Like, what was the actual question?
Okay, sorry, since I don't know the framework very well of the work that you're doing, could you just give some context, motivation for the result itself? Thank you.
Well, I don't know. I mean, one possible application of this work is sort of comparison of different models for these higher category things, but I don't know, my personal interest was not really that. I was sort of, I don't know, I like, this is the sort of thing that somehow should be true, but it wasn't like obvious how to prove it. So like I was sort of, I don't know, like my personal motivation was sort of the problem itself. I sort of found the result interesting. Yeah, I don't know. Does that answer your question?
Perfect. Is there any other question? So let's thank the speaker again. Thank you, Yuki.